Let's dive into semi-structured data, primarily focusing on JSON. Structured data is highly organized and easily searchable with a well-defined schema and a fixed structure. By contrast, semi-structured data lacks a definitive structure, but it provides flexibility. If some customers have extra information, such as multiple email addresses, we can handle it. This data representation is called JSON. JSON, or JavaScript Object Notation, is a commonly used semi-structured data format in web APIs and configurations. It uses key value pairs separated by a colon. For instance, here, cust ID is a key, and 1 is the corresponding value. Good news! Snowflake natively supports JSON with built-in functionality to efficiently store, process, if some customers have extra information, making it perfect for evolving schemas. While Postgres uses the JSON-B data type, Snowflake uses the variant data type to handle commonly used semi-structured data format. The variant web APIs support configurations, and it uses key value pairs separated by key value pairs. For instance, array is an ordered list of values.
Cust ID
we can create a
is a
Snowflake
key,
table with variant columns
and
to handle
1
these varied
is
data
the
types,
corresponding
as demonstrated
value.
in the customer info example.
Good news!
Snowflake's built-in functions
Snowflake
work with
natively
semi-structured data
supports JSON
One such function
with built-in
is called JSON.
functionality
This
to
function
flexibility.
JSON format strings
If some
and
customers
queries
have extra information,
having a
making it
valid
perfect
for
for evolving
evolving
schemas. While Postgres uses the JSON-B data type, Snowflake uses the variant data type to handle commonly used semi-structured data format. The variant web APIs and configurations, and it uses key value pairs separated by key value pairs. For instance,
array is
here,
an ordered list of values.
cust ID
Create a
is a
Snowflake
key,
table with variant columns to
and
handle
1
these varied
is
data
the
types,
corresponding
as demonstrated
value.
in the customer info example.
Good news!
Snowflake's built-in functions
Snowflake
work with semi-structured
natively
data like
supports
JSON.
JSON
One such function
with built-in
is called JSON.
functionality.
Store and query JSON. Let's say we have customer JSON data enclosed in strings. We pass it to parse JSON, which returns a JSON object as a variant data type. Additionally, objects construct can create JSON objects from key value pairs. Here, we pass the keys and their respective values as arguments, all separated by commas rather than colons, of our customer information to the function. It returns a JSON object, as shown. Now that we know how JSON data is stored, let's query it. Snowflake provides a colon notation to retrieve values from specific keys. For example, to access the age, name, and email value from the customer info column, we use a colon to separate the column name and the key. The result will display separate column values for each key. Let's take it one step further and consider nested data. Here, the address shows nested properties like street, city, and state. To query these values from the nested address, we can use either colon or dot notation. Colons separate each level of the nested JSON structure. For instance, we can use the given query to access the street name nested within the address key in the customer info column. Alternatively, dot notation starts with a colon for the first level and uses dots for subsequent levels. Here, we have separated address and street with a dot. The end result is the same. You're now ready to experiment with semi-structured data in Snowflake. Let's dive in.
Thank you for completing the Snowflake course on DataCamp. I'm Gilberto Hernandez, lead developer advocate at Snowflake and a contributor to the course that you just completed. I'd like to invite you to Snowflake Build, our free virtual developer conference taking place globally from November 4th to November 7th, 2025. Build is a great way to learn about Snowflake's latest innovations, including new capabilities in data engineering, AI, and apps. You can register for free at snowflake.com/build. So keep learning, keep building, and I hope to see you at Build and future DataCamp courses.
Hello, and welcome to this course on data modeling with Snowflake. My name is Nuno Rocha, and I'm Director of Engineering at DataCamp. This course was done in collaboration with Margarita Torres, Senior Data Engineer with expertise in establishing foundational structure for data analysis and data science projects. Data modeling is all about organizing data in a way that is both easy to understand and efficient to use. Every hour invested in refining a data model can save countless hours during data querying and analysis. Together, we're going to uncover this essential process. Let's dive in. Imagine opening a closet packed with clothes, shoes, and accessories, all jumbled together. If nothing is sorted, finding a belt or the matching shoes you need becomes a terrible task. That's precisely how data feels without proper modeling, cluttered and confusing. Data modeling is like organizing that chaotic closet, categorizing, labeling, and placing everything neatly so we can easily find what we need. Now let's scale that closet to the size of a shopping center. Can you visualize the importance of organization on such a large scale? Imagine the chaos and the waste of time. This is how vital data modeling is. A data model is a representation, like a blueprint, that outlines the organization and storage of data. It aims to design a well-laid center where everything has its place, and we can find anything quickly and easily. In the context of a shopping center, imagine the entire place, full of shops, is our database. The individual stores are our entities, the tables in the database. Our entities would be a clothing store, a grocery store, an electronics store, and so on. The products inside each store are the attributes, the columns in a table. An attribute of the store's entities would be product price, quantity in stock, brand, etc. And the pathways and escalators connecting these stores or entities represent relationships. Let's look at a single entity from our shopping center, the grocery entity. An entity is a distinct object or concept represented in a data model. These are the tables in a database. What is the grocery entity made of? Which attributes does it contain? Let's describe it. The SQL command describe table, or simply desk table, followed by the table's name will display the structure of a table. By executing this query, you'll see the structure of the entity. It contains elements like product ID, product name, category, price, quantity available, supplier name, and expiration date. They are the attributes. Attributes are the characteristics of an entity. Category, quantity available, supplier name, all these are attributes of this grocery entity. The rest of the columns in the description are the data type and other technical details from this table. For now, we're simply observing the data model, this map or blueprint, to understand what a grocery entity could contain. Let's move into a more detailed examination of a similar industry, e-commerce online retail. This digital marketplace isn't just about buying or selling products online. It's a complex system of inventory, transactions, delivery logistics, and more. Given the complexities of online shopping, you can imagine how detailed its structure could be. In industries like e-commerce, data modeling isn't just helpful, it's essential. It provides the framework, the blueprint, for organizing vast amounts of information in a logical and meaningful way. We will continue exploring this industry's data in the exercise to gain a deeper understanding of what data modeling is. Let's take a moment to review the main concepts we learned. Now, let's practice so we can remember what we have learned. Welcome back. After introducing data models, let's explore the different types. We've learned how to differentiate them and determine when to apply each. Let's dive in. Imagine you're planning to build a house. Before laying the foundation, buying materials, or hiring workers, we should first sketch a rough design idea. With just the basic outlines, this high-level drawing is like a conceptual data model in the data world. It provides a broad overview of what we want to achieve. Continuing with our house analogy, after the rough sketch, we will need a detailed blueprint with information on room sizes, window placements, etc. A logical data model is very similar. It's more detailed than the conceptual model and sets the stage for actual construction. Remember our e-commerce platform from the previous video? Let's apply the conceptual model to it. We will split the data, focusing on primary entities like products, customers, and orders. Considering how these entities relate, we see that customers generate orders, and orders contain products. The conceptual model is a high-level overview of the primary data entities. We do not need more details than that for a conceptual model. Just like when we initially sketched the layout for a house design, we were not thinking about the specific measurements and dimensions of the house. Moving to the logical model, we detail entities with attribute definitions. The logical model will need to describe the attributes of each entity. For instance, for orders, there is an invoice ID, prices, quantities, etc. Orders will include all the attributes generated by the customer. One customer could place multiple orders, generating a new invoice ID for an order. This leads us to define relationships by adding cardinality. In data modeling, relationship cardinality is the number of times entities are associated: one-to-one, one-to-many, or many-to-many. In our e-commerce example, one customer can generate multiple orders. Each order can contain many products, and one product can appear across various orders. This setup indicates a one-to-many relationship from orders to products. This logical model is like the blueprint for our analogy of the house, where we are giving a measurement to each part. Do you recall what the original e-commerce online retail entity contains? Let's refresh our memories. We can run a straightforward SQL query to grasp the available data, which fetches everything from the entity. The results allow us to identify the attributes of the entities we defined previously. For example, there is a customer ID and the country from where this customer is from. For our logical data model, we'll initiate by creating the customers table. To create a new table, we need to know the data types of the entity attributes. We will write the script to describe the table as we learned previously. The result allows us to see the data type of each column currently existing in the e-commerce online retail table, so we can create the customers table following the same structure. Now that we know all the details, let's use the SQL command create or replace table, followed by the name of the new entity and the list of attributes. Upon execution of the create table command, we establish our entity structure based on the logical model specifics. Let's take a moment to review the new concepts we have learned so far. We've come a long way. Next up, we'll dive into the final model, the physical model. But first, let's put your knowledge into practice. Welcome to the deep dive in the third and final type of data, the physical data model. Here is where theory meets practice as we explore how the model is created. Previously, we used the analogy of building a house, starting with a sketch and progressing to the detailed blueprints. Now, it's time to transform those plans into tangible structures. In data terms, this is our physical model, the stage where we craft our entities, attributes, and relationships. Before we establish the relationships between our tables, it is essential to define the data types for each attribute of the entities we have. Let's bring back our e-commerce platform for this. Customers, orders, and products should contain all the attributes defined in the logical model. For the physical model, we have to expand the entities with a more technical detail, adding data types. Data types dictate the kind of data each column will store in the database. Now, we're ready to integrate relationship details technically. A fundamental step in building our data model is to assign a primary key, commonly abbreviated as PK, to each entity. In our model, a customer can have many orders, indicating a one-to-many relationship. Here, customer ID will serve as the primary key for the customer's table. Meanwhile, invoice number is the primary key for the orders table and stock code for the products table. Primary keys help us ensure that each record in a table has a unique identifier that never repeats. In our e-commerce model, we create the products table with a unique stock code as a unique identifier for each item. We achieve this by specifying the stock code with its data type, in this case, varchar 255, as the primary key. This key means each product is listed only once but can field many orders. For example, suppose someone buys a book and 3 pencils. In that case, the orders table has a separate lines for each, all related to our products by stock code. The primary key clause in our table design specifies the stock code as the unique identifier for each product. The next step in the model is to establish connections between related entities using foreign keys, often abbreviated as FK. Foreign keys are crucial for creating relationships between tables. It creates a bridge between tables using each table's primary keys. For example, in our e-commerce model, each order contains various products. We can reflect this in the orders table by reversing the products table through a foreign key that connects to the stock code primary key in the products table. Let's create that foreign key to link the products table with the orders table. Note 2 changes that must happen when you create the table. First, add a new column that will refer to the key of the foreign table. In this case, the data type for the stock code is varchar 255. The second step is to use foreign key and references clause, which defines a column that refers to the primary key of another table, creating a relational link between the two tables. For the foreign key clause, we will use the stock code column created in step 1. And for the references clause, we will use the foreign key table named products and its primary key, which is stock code. We have established data types and relationships in our physical model and are ready for the next steps. Our current model shows updated columns and links. Let's review the essential functions we have learned as we wrap up. Now, let's practice. Welcome to this adventure through data relationships and data normalization. In this video, we will focus on the foundational elements of relational data and the role of keys. We'll explore how these keys work and why they are essential for effective data management. Let's dive in. Here, we see an example of relational data. While it might seem that we have one large entity containing all our data points, we aim to simplify and structure this information. We will learn how to break down this large entity into smaller, more manageable entities. One of the foundational elements of relational data is the keys that define and strengthen the relationships between different data entities. Think of these keys as the vital connectors in a network, much like roads that link various cities. By establishing keys, we will create clear connections between these individual pieces of data. We'll explore how primary and foreign keys help us to build these relationships effectively. Keys, primary and foreign keys, are not just tools. They are the foundation for building our data model. The concept of relational data refers to data neatly arranged into distinct entities. Keys, like primary and foreign keys, are what we use to link these entities together and define the relationships between different pieces of data. Keys unlock the power of relational data with essential benefits. Let's review them. Keys help us structure our data with related entities, safeguarding its integrity, meaning our data is both well-organized and trustworthy. Keys mirror real-world connections, offering a model that captures complex relationships and interactions. They also make data access more efficient, enabling quick and precise data retrieval. Finally, keys are critical for scalability, allowing our model to grow and adapt to business requirement changes while maintaining data integrity and reliability. Let's take a moment to recap. Remember primary keys? A primary key uniquely identifies each record in an entity. In practice, when we create or replace a table, we first define the entity's name, list all the attributes and data types, and assign which one will be the primary key. A foreign key, on the other hand, links one entity to another. To add the foreign key, we need to adjust the script by adding the identifier column and the reference to the primary key of the foreign table. We've highlighted scalability as a key advantage of relational data. Let's manage the entry of new data into our model. In our established physical data model, the products entity comprehensively details each item by its manufacturer. Now that the business has informed us it will add product categories, we must adjust our model to accommodate this. Our next step is to first establish a new categories entity with a unique primary key. Then, we'll link to our products entity using a foreign key, capturing the one-to-many relationship where a single category can be associated with many products. To incorporate the foreign key of categories into products, we'll use alter table command. This command modifies the entity structure by adding a new column with add column, specifying the name and data type. Then, we'll use alter table again to add the foreign key using the familiar syntax of foreign key and references. These alterations will complete the update to the physical data model of products. Take some time to review the functions that we have learned so far. Now that you have learned that relational data will fit very well into the data model in Snowflake, let's practice. Hello again. We will now immerse ourselves in data normalization. We use this approach in data modeling to ensure integrity. We can think of it as tidying up our data, ensuring everything is in the right place and easily accessible. As we explore the data modeling world, we encounter a silent challenge, the unnormalized data, which can also be called unnormalized form, commonly abbreviated as UNF. Unnormalized is when our data lacks a defined structure or is disorganized, where there might be repetitions and anomalies. When examining the all products table, signs of unnormalized data become evident. For instance, the category attribute for bananas lists multiple values in a single row, A plus and A. This anomaly happens for many other products, making it challenging to identify individual products per category. We can also see redundancy in the manufacturer of the product. The fruit assigned to a manufacturer has two attributes that repeat themselves, manufacturer ID and manufacturer name. The ID 104 will constantly be referring to summer harvest, making having both attributes in the same entity unnecessary. Other anomalies are errors in values inserted, or the duplicated products, which indicates this is not a unique identifier for our entity. Unnormalized data presents two significant issues, redundancy and anomalies. Redundancy means unnecessary data repeats, leading to waste storage space, complicating data updates, and inconsistencies. These issues can cause more problems with performance, complicating maintenance, integrity risks, interdependencies, and others. Let's learn how to spot unnormalized data using Snowflake. We have to look for specific patterns, like repeating values or dependencies on attributes that are not the primary key. In our entity, we can use the group by clause to aggregate data by specific columns. Then, we can apply the count function to get the number of distinct entries for each product. Let's name this count as repetitions. By having the having clause, we can filter the results to show only those items with repeated values, helping us identify potential redundancies in our data. Let's select all the distinct category values. We encounter both single and combined categories. A category like L is atomic. However, seeing L, A, AA, or B, L indicates that products can be part of multiple categories. This complexity signals that our data model could benefit from further normalization to ensure each product is linked to single categories. Let's see how these unnormalized data affect us during data retrieval. We will select all products where the category is L. If we look at the results after filtering for category L, we only see the lemon product listed. However, kiwi and raspberry should also be in this category. This case indicates a complexity in how the data is stored and retrieved, making it vulnerable to anomalies during updates or when trying to query data. After exploring issues related to unnormalized data, let's discuss normalized data and its benefits. Normalized data is organized into distinct entities. Each entity represents a single object or concept. It improves data accuracy and reliability by minimizing redundancy. This minimization supports consistency across the model, increasing business reliability. It enhances query performance, allowing efficient data retrieval for quicker business decisions. It also optimizes resource use by reducing duplication and saving storage, offering cost-efficient solutions. Let's summarize the functions we have learned so far. Take note of the implementations of the functions as well. The first query gathers unique values meeting a condition. The second query counts entries per unique column name value, applying a condition. Let's practice identifying anomalies to ensure we can fix them. Hello again. We will now focus on the data normalization process. Data normalization is the process of organizing data in a relational model to reduce redundancy and prevent anomalies during data insertion or updates. Normalization is a multi-step process that ensures data integrity across entity relationships. Normalization involves three forms. The first normal form, or 1NF, targets eliminating multiple values in data. The second normal form, or 2NF, focuses on removing functional dependencies. And the third normal form, or 3NF, aims to eliminate transitive dependencies. We will detail each of these normal forms in the following videos. Let's start with the first normal form. The first normal form, or 1NF, ensures each table attribute contains unique, indivisible values, eliminating repeating groups. Take our all products entity. Its category attribute has comma-separated values. This violates the first normal form because these aren't single categories. In our current unnormalized all products entity, updating a single L category proves challenging since it's not isolated. Querying the category attribute reveals multiple comma-separated values in single rows, indicating non-compliance with the first normal form. Our task is to separate these into distinct rows for each value. To address category values that are not single in their cells, Snowflake has handy functions to rescue us: trim, lateral, flatten, and split. Trim cleans the data by removing empty spaces from start and end values. Lateral, combined with flatten, treats complex lists as tables, separating items into individual rows using split on a delimiter, which here is commas. F value results from this process, where F is the alias for our flattened data, and value is each item. And finally, we specify all products category with lateral to ensure that Snowflake applies these functions to this specific attribute. To achieve the first normal form, we'll create a distinct categories entity using create or replace table. This new entity will ensure each category is alone per row. It includes two attributes, category ID as the primary key and category as a unique value. This setup marks the way for future relationships in our data model. Now, let's populate our new categories entity. We must split and insert comma-separated values from the category attribute into categories entity. First, we use insert into, a SQL command, to insert new rows into an entity. Specify the entity, categories, and the attributes to be populated, category ID and category. We'll then select from the all products entity, extracting the unnormalized data. We use Snowflake's lateral, flatten, input, split, and trim functions to separate the category values and avoid anomalies. For assigning unique identifiers to category ID, we use row number. This function creates a sequential number to each trimmed value. This step is crucial for establishing a unique primary key. Finally, we use group I on the trim values to ensure uniqueness. We have successfully set up our new categories entity with this. To align the entire model to the first normal form, we need to link these categories back to the all products, creating a relationship between them. The categories entity now reflects one step, the first normal form, of the multi-step data normalization process. We broke down the category attribute from multiple values locked in one attribute into individual values. Let's summarize the new functions we have learned in this cheat sheet. Take note of the implementations of the functions as well. Ready to practice the first normal form? Let's go!